The Metropolis Hastings algorithm is a powerful method used in Markov chain Monte Carlo techniques to generate samples from complex probability distributions. It is widely used in Bayesian inference, machine learning, and statistical physics. What is the Metropolis Hastings algorithm? The Metropolis Hastings algorithm is a sampling technique that allows us to generate samples from a probability distribution when direct sampling is difficult. It does this by constructing a Markov chain that moves through the space of possible values, gradually converging to the desired distribution. Key steps of the algorithm. First, we start with an initial value, which serves as the starting point of the Markov chain. Second, we propose a new candidate sample based on a proposal distribution, which determines how we move from one sample to another. Third, we calculate the acceptance probability, which compares the likelihood of the new sample to the current sample. If the new sample is more likely, it is accepted. If it is less likely, it may still be accepted with a certain probability. Finally, we repeat this process for many iterations, building a sequence of samples that represent the desired distribution. Why use the Metropolis Hastings algorithm? Many probability distributions are too complex to sample from directly. The Metropolis Hastings algorithm provides a way to generate representative samples even when the distribution is unknown or computationally expensive to evaluate. It allows us to estimate expectations and probabilities by averaging over the generated samples. Example: consider a case where we want to sample from a probability distribution that is difficult to compute directly. We initialize the algorithm with a starting value, propose new values based on a simple distribution, and decide whether to accept or reject each new sample. Over time, the sequence of accepted samples closely follows the true distribution. Applications of the Metropolis Hastings algorithm. In Bayesian statistics, it is used to estimate posterior distributions when exact computation is infeasible. In physics, it helps simulate particle systems and thermodynamic states. In machine learning, it is applied in probabilistic models and neural network training. Challenges and considerations. The efficiency of the algorithm depends on the choice of the proposal distribution. Poor choices can lead to slow mixing and longer convergence times. It requires a sufficient number of iterations to produce accurate results. Tuning the acceptance probability is important for maintaining a balance between exploration and efficiency. Conclusion: the Metropolis Hastings algorithm is a crucial tool in computational statistics. By using Markov chains to explore probability distributions, it enables sampling from complex models in a wide range of scientific and engineering applications.